Welcome to Microlecture 42. Here we're going to talk in a little bit more detail about sulfonate leaving groups. Okay, so we have seen mesolates and tosylates before. They're these good leaving groups that would take the place of a halogen, for example, if we wanted to think about doing an SN2 or an E2 reaction and generate a leaving group that was stable but not a halide. We have these species, these kinds of species that can serve as leaving groups. Okay, the one with the aerial group here, this one is called a tosylate. This part that I have boxed is a toluene structure, and so we can have a bunch of abbreviations for this type of molecule. So we could call it ROTS. Sometimes you see it, you've already seen it written ROSO2. Could have AR for aerial, or we could have ROSO2PH for phenyl. So aerial is AR, pH is phenyl, and these are just abbreviations that refer to that benzene ring structure. And there are other similar sulfonate structures that don't have a toluene. Another one that doesn't have an aromatic ring at all is a mesolate. Okay, so we have a tosylate and a mesolate as leaving groups. Abbreviations here would be OMS. Okay, so when we see MS as a group, we're talking about a mesolate. The other way to write that out shorthand is OSO2CH3. So let's draw out a sulfonate structure and think about the reaction that could occur, maybe with cyanide, which is a good nucleophile. Remember, the cyanide being a weak kind of species would like to attack carbon if it can, and so when it attacks this carbon, it's going to kick out the negative charge onto the oxygen of the sulfonate, generating the major organic product we know, but let's focus on sort of byproduct here, which is this. And it turns out we can draw all sorts of resonance structures. We can draw resonance here. Okay, and then there's one more resonance form yet with the negative charge on the bottommost oxygen. So plus more resonance forms. And so we've got a lot of resonance stability of our leaving group, which is going to drive the reaction in that direction. So that's why they're sometimes a more favorable route than using an alkyl halide. So let's take a look at a couple of reactions of sulfonates. So when you see sulfonate as a leaving group, it does not mean that you're necessarily doing SN2 or E2. It's a good leaving group in a variety of different mechanisms. So let's look at two situations. One in which we have an acetate ion, okay, which is it's a weak base or a good nucleophile, right? So being that it's so stable, it's not a strong base that would want to attack a proton, and so immediately when we're seeing this resonance stabilized nucleophile, we're thinking of it as such. We're thinking of it as something that's going to attack carbon, not a strong base that would go for a beta proton. Let's do another scenario where we have a mesolate, and notice these are both secondary leaving group situations, and so we've got to figure out, based on what our nucleophile or base is, what type of reaction we're doing. So if we have a hydroxide, now I'm thinking strong base, not nucleophile. And so the way I approach these reactions is going to be different. So with my good nucleophile, I'll attack from the opposite face of the leaving group and kick out the tosylate. So for this problem, I would predict the inversion of stereochemistry, and it would look like that as a product. And for the strong base, I would find a beta proton and kick out my leaving group. That way it would be a E2 reaction forming the alkene. In this case, our alkene is conjugated, so it has minor resonance forms contributing to its stability. Okay, so in one case, we're seeing an O-tosylate being kicked out, but it's happening via SN2 mechanism. And in the other case, we're seeing a mesolate structure being kicked out as a leaving group, and this is happening via E2 mechanism. So these sulfonates can be synthesized, and these are some reactions that you're not going to be responsible for the mechanisms. I'm not going to ask you how this chemistry occurs, but you will have to be able to identify when this is happening just based off of the reagents, and be able to predict the products accordingly. So something that we do in synthesis a lot is we start with an alcohol and we kind of generate something that has a better leaving group than the alcohol, right? And so we have a poor leaving group, and we generate this good leaving group to do further chemistry. The way we do that is by adding what's called a Tosyl chloride. This Tosyl chloride basically just looks like this. So it's the same structure we had before, but it just has this chlorine atom where the oxygen was. And that chlorine atom is displaced, okay? And the sulfur that it's bonded to ends up being bonded to the oxygen to generate the Tosylate structure, okay? So this is the same thing as the reagent set is the Tosyl chloride and pyridine, which is a reagent that looks like this. Like a benzene ring with a nitrogen atom inside of it. Again, no mechanism here. You're not required to know the mechanistic details, but you would want to be able to predict the product. So another example then is if I gave you an alcohol, and I said, what are the products when we react with mesyl chloride and pyridine, right? And so we know that we're going to essentially turn this alcohol into a sulfonate structure. So I'm going to redraw everything about this molecule. The new bond that formed was between oxygen and sulfur. So it could be drawn like that, or we could just abbreviate it as a mesolate.